Hello and welcome to another episode of the Project Purple podcast. I'm Dino Verrelli, founder and CEO of Project Purple. We have an exciting interview coming up with a very special guest after a few quick updates. Since 2010, we've contributed over $3 million and counting to pancreatic cancer research efforts. We've also allocated over $1,500,000 to more than 1,300 patients and families through our patient aid programs. Your monthly or one-time gift can improve patients' lives through research and assistance programs. You can donate now at projectpurple.org. Pancreatic cancer does not rest, and neither will we. Your support is truly appreciated. If you're looking to get involved in one of our events, whether that means joining a running team, participating in a virtual run walk, group fitness, golf, or anything else you can think of, visit projectpurple.org/events to learn more. Without further ado, let's meet our special guest today. As we record this here in Connecticut, it was -9 this morning, and coming to us all the way from, I'm sure it's not -9, but a very beautiful place in the country out in La Jolla, California, Dr. Cosimo Commisso, who is the interim director, deputy director, NCI-designated Cancer Center, professor of cancer metabolism and microenvironment program at the Sanford, Burnham, Prebys Medical Discovery Institute. Welcome to the Project Purple podcast, and also a fellow Italian. We don't have many Italians on the podcast, but it's awesome to have you here. Thank you for joining us.
Thank you so much, Dino. It's an absolute pleasure to be talking to you today.
Well, I know we were getting to know each other in the kind of the pre-show before we hit record here, and as I said, I get really excited. I mean, all the guests are great. There's been one guest that I don't think we ever aired the episode, and I think I wasted like a lot of time with this person, but that's another story another day. We won't go down the road. I love having all our guests. We've really been blessed with the podcast, but something that gets me really excited is when we bring on people on the front lines, the researchers, the clinicians. I call them all clinicians because I feel like, I know that's not a proper term, but from the researchers in the labs that have labs or that are working in labs, to the folks meeting with patients, the oncologists, the surgeons, the radiation oncologists, all facets of the medical system that are in this fight against pancreatic cancer just gets me really excited because, another big part, and, I mentioned in the opening, and I know we talked a little bit about it, is us as an organization funding research. I mean, that's how we're going to change this game of, survivability in this space is, by supporting researchers like yourself, who are, again, on the front line. So super excited to have you here. What is tradition, as always, on this podcast, the first kind of couple minutes is always the guest opportunity to kind of share their background. We hope you share this with your lab and your friends and your family, but we've got a pretty vast audience. So this is kind of your opportunity to kind of introduce yourself. Tell us a little bit about yourself, maybe a little bit about background, where you came from, where you did your schooling, and how you got to, where you are today. So with that, the microphone is yours.
Sure. Thanks, Dino. So I'm originally from Toronto, Canada, and I did my PhD there in something that you might find surprising. So I actually did my doctoral studies in looking how sense organs develop in the fruit fly, organism called Drosophila melanogaster. I actually want to tell you a little bit about that because it's interesting how that led me to what we're doing now in pancreatic cancer. So during my PhD, I was looking at how a process called endocytosis, which is something that cells do when they need to take things in from the outside and bring them in. And I was looking at how that interplay in the cells during a developing organism was contributing to how the adult structures were going to be finally formed. So we were looking at eyes, and we were looking at different sense organs in a fruit fly. And those pathways that I was studying are conserved all the way to humans. And so there was there were a few critical events that happened during my training that kind of drove me in a little bit of a different direction for my postdoctoral training. So during my PhD, my mom was actually diagnosed with breast cancer. And so, my family was going through that. And, I still love developmental biology, but that entire experience kind of made me rethink about what I was doing on a daily basis. And I said, well, I want to do something that has a bit more immediate impact to disease and just humans and health in general. And so, that would be quite a leap from what I trained in. So I said, well, why don't I find out who's looking at these pathways, these molecular pathways that I'm studying in flies? Who can I train with, or where can I go to apply this in a more relevant human setting and disease setting? So, in just doing research, I kept coming up with a group at NYU. And so that was Dr. Daphna Barsagi's lab. And they were looking at, and interestingly, the pathways that I was studying in the fruit fly are absolutely critical to pancreatic cancer progression. And so I said, so this would be a great platform for me to get into, to have more impact in terms of disease. So after the PhD, picked up and moved to New York City and started training there at NYU. And was there for about 6 years, great environment. And what was interesting is the endocytosis that I was working on in the flies, we ended up going on to show that a slightly modified form of that endocytosis called macropinocytosis is absolutely critical in pancreatic cancer for the tumor cells to get nutrients from their environment. And so that made a big splash at the time. And when I was ready to, get my independent faculty position, started to evaluate where to go. And I ended up here in California. And so that was over 10 years ago that I moved here in La Jolla and started up my lab. And now we work on a lot of different things. We still work on that concept of nutrient, how pancreatic cancer cells get their nutrients from their environment through this endocytosis pathway. But over the years, I get really interested in things that impact pancreatic cancer very easily. So every time we have a small discovery, it takes us in a slightly different direction. But so we started to look at things like pH. So how an acidic versus a basic environment in the tumor really affects tumor progression. And really recently, we've been starting to get into how age of a person impacts pancreatic cancer initiation, progression, and we hope in the future to study how age will affect therapeutics. And so that's how I got into pancreatic cancer, but I want to tell you what keeps me in pancreatic cancer. So I haven't had a personal experience with having a family member have pancreatic cancer. I've had, as I mentioned, my mom was doing fine. She had breast cancer. My grandfather passed away from colon cancer. But in having different events and different experiences with organizations like yours, Project Purple and others, I really started to see that there's an unmet need. So a prognosis of pancreatic cancer, as everyone knows, probably listening to this podcast, is not good, and we need to do better. And so the lack of survivors, the lack of the lack of funding to the disease, it just made me become passionate about it. And so that's why we've been having our research really just focus only on pancreatic cancer now for 10 plus years here. And I think I obviously am a little biased, but I think we've been doing great. Now the next step would be to translate, I hope, our fundamental findings that we're making to really give back and have that patient benefit, that clinical benefit.
Wow. Well, thanks for sharing that. I mean, I think that's we were connecting the dots before we hit record. My motivation is, my dad and, how this has evolved. But I'm always super fascinated, especially from the science and the medical side. Like, why do people get into it? And not everyone has a connection, but I know we were talking a little bit about funding, and there's many other diseases that get further funding.
Yeah.
So it's really inspiring and awesome to have people like yourself, in this space day in, day out, doing this discovery because we need it. We got to do it. I mean, I think that's one of the things, and I've talked to so many people. I feel like there's so many positives happening. Clearly, it's for a lot of the folks. Unfortunately, and I don't think this is. There's never going to be a perfect timing, right? For some folks and stuff, but there is a lot happening, which is good. But I think the other piece to this, and I'd love to maybe go here next, is just the complexity of the disease,
Mm.
right? This is something that I hear often is like we get to this point where we think I remember seeing a presentation at AACR maybe 10 years ago, and it was like, or it was probably like a couple years ago, but they were going back to like 10 years ago. This was the pie of what we thought we knew. And it had like 5 slices, and now the pie is like 25 slices, right? So as soon as we open one discovery, there's 10 more that open up potentially. So let's
Yeah.
talk a little bit about that, especially in your space, as you
Yeah. The
guys.
complexity of the disease.
Yeah.
So, I'll let you know that we do predominantly use our animal models as our bread and butter for our research. But we do dabble in making sure that what we're finding in our fundamental studies are relevant to the human disease. And we do that with our clinical collaborators. So everything we do is validated in human patients, human samples. And in terms of the complexity of disease, obviously we don't see this in humans, so we're not able to see how early the complexity starts. But when you look at the animal models, and if you can extrapolate that to people, I mean, we can certainly discuss whether that's true or not. But in general, I think you can. And what we see is that there's tremendous complexity throughout the progression of the disease. And so maybe I can make some comments on some of the things, the complexities that we have been observing, and how we see those as obstacles that we have to try to overcome if we're going to develop novel therapeutics. So you probably have had people talk about the stroma on the podcast. And
which is that outer layer of around the cells, right? That are the cancer.
Exactly. So the tumor is made up of tumor cells plus all of these other cells and the things that they produce that are recruited into the tumor, that are not mutated like the tumor cells generally, but they produce all these collagens and these molecules that kind of make increasing the stiffness of the tumor. They make them really, really hard. In terms of just how they feel relative to a normal tissue that's nice and soft. And so this gives a lot of challenges to delivering drugs. And if we can overcome some of that, probably we'd be able to increase, the dosage of drugs that get into tumors. And so our lab has been looking at this from the metabolism standpoint. So it's the tumor cells have, and I'll mention that next, the tumor cells have this really unique metabolic requirements, and they have all these different pathways that they use to survive in the tumor, because the tumor itself is not a very pleasant environment. It's really harsh. It's really acidic. It has low nutrients. It's hypoxic. There's a lot of what we call cellular stresses in a tumor. So the tumor, in order for it to grow, it has to overcome these things. And so what we've been looking at is how this stress actually impacts the stroma. And so we've had publications, and we're working on some that are going to be coming out soon, hopefully, that shows that it's not just the tumor cells that have these complex metabolic activities. It's also what we call the stroma cells. And a lot of those are fibroblasts. And so if we can now maybe learn a little bit more about the metabolism of these fibroblasts, we can start to augment and change the stroma to benefit what we want to do, which is to reduce tumor burden. And so, in our studies, what we found is when when we play around with the metabolism in the tumors, we can actually affect the stroma in a way that then sensitizes the tumors to standard therapies. And again, this is all in animal models. And we hope to translate it, once we establish, the parameters in the animals. It affecting the stroma through the metabolism really sensitizes tumors to chemotherapies. We've tested just a simple, gemcitabine, which is, very, very standard, chemotherapy. Additionally, what we've looked at is to see, because immunotherapy is really going to be the thing, in my opinion, that eradicates a tumor. And so we have also seen that affecting the metabolism of the stroma can sensitize the tumor cells to immunotherapy in these pancreatic models that we use. So we're really excited about that, and we need to see what are the best ways of now translating this for patient benefit. So the stroma is one example of the complexity. The other thing I'd like to mention is a concept that's called metabolic plasticity. So these tumor cells are really resilient. You can throw them different metabolic or nutrient stresses, and they adapt, which is one reason why it's been really, really hard to sort of go after these targeted therapies, at least from the metabolism perspective. For example, you can reduce or get rid of a specific nutrient. The cells will sense it, and then they will adapt accordingly and totally rewire their pathways in order to continue to grow and become somewhat independent of that specific nutrient. It's a huge challenge. And, generally, and when you're doing fundamental science, and then also when you want to translate and take, a therapy into hopefully into patients, the predominant thought is that the more specificity you have, the better. But we kind of fell into something last year and was published last year, that we took advantage of something that was not very specific. So what we did was we had, so one nutrient that we study in the lab is glutamine. And so glutamine is an amino acid. It's the most abundant amino acid in circulation. But in the tumors, it's actually lower than normal tissues. And the reason is because the tumor cells, they use it up so much that the consumption of this specific nutrient then ends up depleting it from the tumor microenvironment, or from the tumor as a whole. And so these cells are eating up this glutamine, using this glutamine to drive their growth. And then they start to do other things and adapt to low glutamine, but it's still critical. No matter where you get the glutamine from, it's critical. And once this amino acid gets into the tumor cells, different enzymes use it for a lot of different things. They use it to make lipids, they use it to make proteins, they use it to drive cell division, they use it for a lot of things. And the targeting of an individual function of glutamine has not really borne anything clinically. And this is because the cells, one, can adapt, and two, it just has so many roles. So we came in, we found actually this molecule had originally been shown to have anti-cancer properties. I think it was in the 1960s or so. And, we kind of revisited it, we kind of fell onto it. So what it does is that it's a molecule that looks like this nutrient. So it structurally, it looks like glutamine. It's called DAWN. And it looks like glutamine, but it's not glutamine. And so what happens is when an enzyme tries to use it because they think it's glutamine, it gets stuck. And so the enzyme doesn't work. So it comes down as a hammer basically on the cells, and any enzyme that then wants to touch glutamine gets clogged and blocked. And so we showed that in our preclinical mouse models, that this was actually a really, really good molecule to use to diminish tumor growth. And we figured out how it was working in pancreatic cancer. And so that challenge of what I refer to as metabolic metabolic plasticity, which just means that the cells can adapt and change depending on their environment. That can be overcome actually by reducing the specificity of some of the molecules we're using. So in this case, having a less specific therapeutic actually was beneficial.
So listening, and I am taking notes here. So it's almost like I'm trying to like relate this to like, and I wrote down here like a diet for the tumor, like and correct me if I'm wrong. Like, so if we could give the tumor a specific diet, but then what you just said in terms of metabolic plasticity, if we know that this enzyme clogs the tumor or clogs and it's clogging the stroma or the tumor, that
the molecule is clogging the enzymes that are using a specific nutrient.
So could we replicate that molecule to like allow that to happen like automatically within the whole environment, and then allow therapeutics because of this diet that we're putting the tumor on to get a specific response?
Yeah, so so we hope that our studies that had come out was one of the first to come out to show how this molecule is working, and maybe put it on different folks who are developing these molecules for therapeutics. Put pancreatic cancer on their radar, because right now my understanding is they're looking at lung cancer and other cancers, and so that's sort of what I see our role as, my role as. So as a fundamental scientist, if I know something is working in a different cancer, or if I see something that's working in a different disease, or I see something new that we discover, let's see if it's applicable to pancreatic cancer, and then try to bring that to the forefront, so that if there are clinical trials happening, then pancreatic cancer patients could be enrolled in some of those.
Love it. I love seeing the science cross, right? Because could work somewhere else, or seems to work but then doesn't, could work in another space.
You never know unless you try.
Yeah, and I don't think we've tried enough, right? Like, and clearly there's not enough being done, and that's not a knock on anyone. I'm just saying as a whole. So I've got a question. This is like I get a lot of loaded questions here.
Okay.
So understanding, metabolism of the cells and things that kind of contribute to progression and within, the disease of the cellular level, and just staying with within a metabolic state, I guess. And, I always, like the analogy I use is like with our bodies are like engines, right? And if you have a Ferrari, we're Italian, you probably don't put 87 in it. You got to put
I don't have a Ferrari though.
I don't either. Okay. But, we can relate to or a Lamborghini, right? I was in Italy a couple years back, and we were we went to the Ferrari factory at Two Boys, as I mentioned. Had to go to Ferrari factory. So we went to the Ferrari factory. And, there's these beautiful cars. They're worth hundreds and hundreds of thousands of dollars, millions of dollars. But, they use specific fuel to keep them running at such a high level.
Yeah.
And you use specific oil, to keep everything, proper. This is a loaded question, but so do you think in your 16 plus years of being in this space and understanding metabolism and, cells and this, we have seen an increase in disease. I know there's been some data recently about younger cases.
Yeah.
Do you think, again, using the analogy of an engine, I'm always curious about what we're putting into the engine that is causing and it may not be causing cancer, but like causing inflammation, causing obesity. We know obesity, right? We know smoking, like people who smoke, like it leads to a lot of issues, a lot of, cancer potentially, and a lot of other health issues. Not having a well-balanced diet or eating certain kinds of foods, we know will cause some sort of metabolic issue within your body and some sort of inflammation and some sort of causes. So, with that being said, in your experience, like if we continue to go down this road of like ingesting certain things that are not necessarily good for our bodies, do you think that's like a cause for concern in terms of where we are, from a cancer like development standpoint?
You're right. That is a loaded question. I think that what you're highlighting is something that's actually increasing in terms of, especially in the media, but also in science, is systemic effects, and in terms of whole body physiology, how that impacts tumor initiation, tumor progression, and also therapeutics. So, I think that it's a balance. I think that there's obviously benefits. People have shown benefits to exercise. With exercise, people have been shown benefits with certain diets. I think that there has to be a consideration for the individual patient, though, because more exercise and better diet isn't going to work for every person if they have a BRCA mutation or something like that.
Yeah.
So I think we do have to be careful about how we overlay sort of these concepts on the population. But I do want to give you a bit of an anecdotal story of how we started to get into the systemic biology, and we said, okay, what is something that's the characteristic of the person or the animal in our case when we study it that we could maybe shed some light on and have some patient benefit. So, we started to look at things in the lab. We said, okay, what can we manipulate? Okay, so we're not in a clinical institution. We're not going to do diet in people. We're not going to throw people on treadmills. We're not going to check their smoking, right? What can we do? So with our mouse models, we said, well, there are a couple of things we could do that could be extrapolated potentially to people. And after talking about a few different characteristics, we ended up on age. And age, inflammation is hugely associated with increased aging. So the older you are, the more inflammation you have within your body, within your tissues. And so we said, okay, well, let's do a simple experiment. And this is all unpublished, but I'm happy to share it. I mean, we've presented it at pancreatic meetings, etc. So we said, okay, well, let's take old organisms, young organisms, and in these animals, and look at pancreatic cancer progression. And it wasn't too much of a surprise, actually, for two reasons: that it was that tumor progression was accelerated in older animals. The reason why it wasn't so much of a surprise was, number one, it has been shown for other cancers such as melanoma, and that if you look at the patient population, pancreatic cancer patients, their average age of diagnosis is around 70 to 72, and that is about the third oldest set of patients in terms of diagnosis. There's only two other cancers that have older average age of patients at diagnosis. So I think that this information is telling us that there's something happening with aging that increases the likelihood of a pancreatic cancer diagnosis. And in the animal models that we used, we saw that this was true as well, which means that we can use these models to kind of better understand what is happening in an older organism versus a young organism. So we're kind of taking a jump into this. It's a new area for us, but I love getting into new areas. It can kind of be challenging because people want you to stay in your lane.
Yeah.
But as I get older, I'm tending not to care as much about that. And so what's really interesting is we're seeing metastatic metastasis really, really being associated with age. And so to comment on what you said about the young, do you have a question? You look like
yeah, but that's due to the inflammation that you're seeing in
well, we don't know that. We don't know.
Okay.
So we know that there is increased inflammation in general with age. We know that pancreatic cancer progression is accelerated with age. But now to link those two, or to link the effects of age to anything else, I mean, that's an open question.
Correct.
We don't know. I mean, obviously, inflammation is a candidate.
Correct.
Right. And we're starting to look at, and the inflammation, I'm glad we're on this topic because I think it could be critical. The inflammation could be a main component of it. Certainly for, maybe not for the actual growth of the tumor, because that's what we've seen, but probably for the metastasis. So we've done all these little tricks where we try to see if we can rejuvenate the stroma in older animals. And what we've seen, it does reduce the metastasis. So if you have a way, so what we're doing right now is we're actually putting young stromal cells into old animals, and we're testing the effects on the tumor, and it suppresses the metastasis. Now, therapeutically, you cannot do that. So you can't implant a young fibroblast into a patient that's old. Like, you just can't do that right now. But if there are chemical ways to do a classic rejuvenation of the stroma at the molecular level. So by definition, the word rejuvenation is that you take an old cell and it becomes young.
Like a CAR T therapy?
Well, it's more through like epigenetics. So by definition, there's certain genes that are expressed by an old cell versus a young cell. And so you can classify something young or old based on that. But if there's a way, and we don't have this yet, but if there's a way to make an old stromal cell in a tumor younger, you could make it become something that could control the growth of the tumor. Now, I want to highlight that this is extremely speculative.
Yeah.
It's solely based on preliminary data that we're putting together for publication now, but we're putting it together. It hasn't been peer reviewed. So I just want to highlight that. But it's extremely exciting. And we did just get our first National Institute on Aging grant to study this. So we're very excited about this area. But it's an example then that I'm using this as an example to show how systemic biology, and the characteristics of the patient matter.
Yeah.
So you may not necessarily want to treat because you mentioned about it being diagnosed in younger patients. So you may not want the same therapy if a patient comes in and is 55. You may not have, and in this case, young is sort of 55, or 50. Yeah. So if you have a patient that comes in that's let's say 45 to 55, you may not have the same therapy as someone that comes, or the same approach as someone that comes in that's like 65 or 70.
Yeah.
Right? So the age of the patient, we think, matters.
So it's so fascinating hearing that, because again, being a patient advocate, and we deal a lot with patients, I can't tell you how many times, and again, I'm not trying to throw anybody under the bus, but I am going to make a point here is we get 40-year-olds that are on the same protocol as the people that are in their 70s, right? And I've always kind of questioned, it's like the more the more complex this becomes. And I feel like eventually everybody's going to be on some sort of like, I wouldn't say, I guess like we got to be careful with terminology, but I know like, they were talking about personalized medicine, for a while. That was like the big buzzword, right? And I think New York Times did a big article on it, I think 2 years ago about like, the impact of personalized medicine and stuff. But if you really think about it, like I think eventually we are going to get to a point where we're going to need to be able to, because of the complexity of the biology of the disease, in some ways to really have like a personalized approach for each individual patient then potentially.
Absolutely. I will give you a piece of data that we've been generating that kind of supports what you're saying. So from a diagnostics point of view, again, this is also unpublished preliminary work, in our preclinical models that we're using, we also were profiling their blood. So animals that have pancreatic cancer that are young versus animals that are old. And what's circulating in the blood, there's a lot of overlap, but there's a lot of differences. So what that tells us, again, we don't know if this can be, we validated actually some of it in patients, but what this tells, but it's still highly speculative, right? But what this tells us is that maybe if you're developing a diagnostic that's based on a circulating factor that's in the blood, you may want to tailor what you look for based on the age of the patient. And I would argue, because we're also starting to look at this, the sex of the patient. So who the patient is will likely affect what you do from a diagnosis perspective, from a therapeutics perspective. I think we're really, really far away from actually doing things like that. I would love to be wrong about that. So hopefully if I hear about something, I'd be very happy. But I think that's the direction that it's going, right?
Yeah.
How the characteristics of the patient, how the systemic biology affects the tumor initiation, progression, diagnosis, therapeutics, all of that, I think is going to be something really, really in the future that we focus on.
And we've been talking here for almost 35 minutes. And I think if anything, this just validates, and I've always said this, like my own personal experience, like patients have to go to high volume centers at the end of the day. Like, and this is just me as the patient advocate speaking again, not to, put down on any other center, but like if you're not going to a high volume center, and there are plenty of groups in this space that will help you get there, PanCan, has a number, they will get you hooked up with one of those high volume NCI designated centers. I think if anything, this conversation here, Cosimo, has like, that is the proof in the pudding, like going to like a regional cancer center or like not a high volume center, that you're not going to get expertise like what we're talking about, or opportunities where, someone there may be thinking the way you're thinking in terms of how do we beat this thing, right? What are some of these things to think about? It's just really, really, there's a lot of work to be done, but I'm also really excited because this conversation is really, really cool. I think it's this stuff. We could talk for hours upon hours on this. I know I want to be respectful for time here, so I've got
again. This is all. I'm all new to this, and again, like people will say, stay in your lane, but I don't think that we have big discoveries and progression by people staying in their lanes. No. So. Unapologetic about that.
But that's how the discoveries happen though, right? Like it's trial and error. And, if you stay in your lane, what's the definition of insanity? Doing the same thing over and over again and expecting different results. Like, I feel like we're in this insanity a little bit, like we've been doing the same thing for the last like 30 years and it hasn't seemed to work. So, couple questions left for you here. Given your experience, where you are professionally, and this relates to pancreatic cancer and what you see, what do you think we do really, really well And this is like from a global perspective, not just
Okay.
like maybe, but what do you some things that you think this space does really, really well?
Collaborate. I think that and we discussed this a little bit before.
Yeah.
Pancreatic cancer community is sort of a unique community in the sense that we're very, very focused.
Yeah.
And we tend to, not that we don't see other cancers as important, we do, but we care more about, we care most about what's happening in our space. And so, as you mentioned, I've been in this for just over 16 years. I hadn't done the calculation in a while, but over the years, I've had the opportunity to interact with, and I'll give a couple of examples, but I've had the opportunity to interact with clinical scientists, translational scientists, other fundamental scientists like myself. And there's always that openness, which is in part one of the reasons why I'm not afraid of talking about constantly about unpublished and unpeer-reviewed work, because the more you get it out there, you not only get compliments, but you also get criticisms from the community, and those are constructive criticisms. And so I would say that one thing that pancreatic cancer does as a whole really well is collaborate. And I really do feel that if there's a blockbuster discovery that could move, the needle significantly in the space, that the community would be on board and the community would all be behind it. Just it's been tremendous also, moving. So when I moved here from New York, I barely knew anybody. I think it was the second week I was here, I knew two people and two other scientists. And I ended up, the second week I was here, I went to go see this pancreatic cancer surgeon, Andy Lowy at University of California, San Diego. And he met with me and we said, we had met maybe once or twice. And now we've been running a pancreatic cancer research group for like about 9 years together. And those sorts of experiences have been just amazing. Other examples, we've been working with UCLA. We just published a paper with the pathology group there. Again, we always want to validate in the patient samples, and so it's been honestly nothing but collaborative experiences. And so I think that's probably, at least from my perspective as a fundamental scientist, that's what I see as the thing that pancreatic cancer community does fantastically.
I love it. I love hearing it. All right. So on that same kind of thought process, but this is, I think, a little bit harder. What could we do as a space better? Where do you think there's maybe areas to improve upon?
Yeah, there's so many areas, but not just pancreatic cancer, but just even cancer in general. But you're right, it's tough to pinpoint one. I think that, and I might get some slack for this, but I think that, people have been making discoveries, and some of the pancreatic cancer researchers in this country are some of the top general researchers in the country. So it attracts this disease space attracts the best and the brightest because of the challenge of the disease, right? Yeah. And I think that people have made amazing discoveries, but we've moved the needle a little bit. Like when I first started, my first day at NYU was the day that President Obama was elected. And I said, we're going to move to this country and we're going to try to make a difference. It was about 5% survival rate. So now we're at 12.5, 13%.
Yeah.
And so, yeah, it's definitely improved. I don't know that it's been improved at the level that people like yourself would want to see it improved at. So what we haven't been able to do is really, really push the needle in a significant way. And there's lots of reasons for that. But I think that one thing would be that a lot of the discoveries that we make in the labs are, obviously we have the limitations of having to work with animal models, and they're great. They're fantastic in terms of, some of them are great in terms of recapitulating the disease. But, we're not taking into consideration those patient characteristics. You can't model race in an animal. You can model other things. You can model sex and age, like I mentioned. But a lot of the models that we're using, they're really, really far away from the characteristics of the patient. The typical patient might be older, overweight, certain demographics in terms of race, maybe a smoker, those kind of things. But the animals that we use for the discoveries, even though we've got a lot of information about the progression of the disease, but in terms of the therapeutics, they're really far away, even on an organismal level, from what the average patient comes in as. So again, I don't want to be too controversial on that, but I think what we could do is we could start thinking a little bit more about the preclinical models that we use. And I think it's been going in that direction, absolutely. So this concept of moving away from animals and going into patient organoids, that probably is also a good thing. But I think what we need to do is we need to have a multifaceted approach to this. I don't think we should drop animal research for organoids. I think that what we can do is the organoids complement the animal research, and then we can make the animal research maybe as best as possible reflect what the patients that are coming in at. And people are doing this. People study obesity. People study smoking. So people are studying all these different systemic effects on pancreatic cancer. But I think that what we have to do is make it a little bit more mainstream, especially from the therapeutics perspective.
Yeah, and we need a big influx of cash to do that.
Yes. So, funding. I don't know. We don't know what direction it's going in right now, but funding is an issue, and in order for us to continue to make discoveries on the initiation side, so what drives pancreatic cancer initiation, what drives its progression, how does it happen? And then number two, the translational part, or the early stage drug discovery part, where we then use what we learn and develop new therapies. We need funding for that.
Yeah.
And research is actually getting more and more expensive. Just like everything, just like
everything's
what is it? Yeah. The cost of eggs or whatever.
Yeah, so, eggs are $9 a dozen, I guess.
Yeah. So that's also reflected on the research side. And so, for example, like the baseline amount that you can request, from the NIH for a modular grant has not changed in donkey years. I don't know the exact years, but.
So you mean to tell me that inflation's occurred, but the government hasn't increased what they pay out? That's a shocker. Yeah. And the other piece there, and this is, I guess this is a joke. This is a joke, but I know I'm sure in your conversations, you've encountered some people that say, oh, you have to get paid, your salary, people have, we have to, people have to make a living, a good wage living in order to do the research, right? So we have to keep that in mind as well, along with the increase on eggs and gas and housing and all that, right? It's almost full circle. It's an interesting situation that we're in currently with so many uncertainties from the government. But I think that, again, from the very beginning, this inspires me to have this conversation. And this just is for us and for the folks listening at home, this is why we have to continue to fund, researchers like yourself and labs and continue to do this, because we are progressing. We need this shot. We need this shot.
We just need it to go faster.
Yeah.
And to make it go faster, because, a diagnosis, you might have 6 months. Correct. Pancreatic cancer, doesn't care how long it's going to take for me to get a grant.
Yeah.
Like, it's going to happen. And so we have to adapt to that as opposed to the other way around.
Correct.
So we have to move faster. And the only way to move faster is by getting faster and larger infusions of money to really drive the research that we need to do to get us where we want to be, which is many, many more patients, many that survive, many more survivors.
Philanthropy is key. I'm preaching to the choir, but for those listening and watching, I've got one last question for you, and we always end every podcast on this question, and this is the loaded of loaded questions.
Oh no! Okay.
Given your experience and what you have gone through, again, we're sitting at a cafe, we're meeting for the first time, or at a bar. What's your definition of pancreatic cancer? Given your experience and your training, your education, how do you define the term pancreatic cancer?
That is a tough one because we're always so thinking about how to tackle the disease and the complexity of the disease that we don't take the step back and say, what is pancreatic cancer? For me, pancreatic cancer is, I would say, it's a dysregulation of the tissue that leads to, and this is going to sound really full of jargon, that leads to,
right or wrong,
that leads to irregular or unchecked homeostasis. So the tissue has a homeostatic baseline, which is this is the nutrients we want, this is the pH that we want, this is the amount of inflammation that's acceptable for a normal tissue. And then pancreatic cancer, a switch happens, and those homeostatic things that are regulating that homeostasis change in order to favor something that shouldn't be growing, that then puts the host, which is then detrimental to the host.
Perfect. Dr. Commisso, thank you for all you do. Thank you for allowing us the opportunity to share all the stuff you're doing there in La Jolla. And you know, we've got to continue, as I said, to fund research. This is critical. People like yourself throughout the world that are going to make a difference in this space. And we all have to work together. This is not, like I always say, regardless of the group, regardless of the institution, we need more people, right? We need more groups. We need more families. We need more philanthropy. We need more scientists. We need this shot, right? And I from day one, I've always said, like, there's not going to be one person that's going to be responsible for this, but if we all get on board, and I think we're getting close to that, right? We can do some really, really great things. If someone watching or listening, something sparked their interest and they want to learn more about what you're doing there in your lab, I know you've got a website for your lab. Is that the best place to send them? I think you're active on X. We don't call it Twitter anymore, but X. I have. That's how we connected. I found you on X.
Yeah, I know I've kind of moved to Blue Sky now, but I still have the X account. Yes.
I know there's a lot of. It's kind of fascinating because maybe because we're just in it, but like I feel like the scientific community on X is pretty active for this space. Yeah. I do see other science stuff, like medical stuff, but maybe just because the way my algorithm feeds, it's always pancreatic cancer, which I love, but I love seeing that. Yes. Yeah, it's awesome. So where's the best place for people to connect with you?
Yeah, you can find out more about what my lab is working on and how to get in touch with us at www.commissolab.com.
And that is spelled COMMISSO
lab.com.
Beautiful. Thank you for allowing us the opportunity to share all the great things you're doing in the pancreatic cancer space here on the Project Purple podcast.
Thank you so much, Dino. It's been so much fun to talk to you today.
Thanks for listening to another episode of the Project Purple podcast. If you like today's episode, feel free to share this episode and make sure you subscribe to the Project Purple podcast either on YouTube or wherever you may be listening to podcasts. That's a wrap of another episode of the Project Purple podcast. Thanks for listening and be safe. Till next time.